Let's take a close look at cellular respiration, which is an example of a catabolic process. It is the breakdown of glucose to provide energy in the form of ATP. Cellular refers to cells, and respiration refers to breathing. When we breathe in oxygen and breathe out carbon dioxide. The cell is no different. Oxygen goes into the cell and carbon dioxide comes out. So what is the purpose of all this? The purpose is to break down glucose to provide energy in the form of ATP. So the overall process of cellular respiration is written as glucose plus 6 molecules of oxygen gives you 6 molecules of water, 6 molecules of carbon dioxide, and 36 ATP. Now the glucose is the fuel that the cell needs and breaks down. And the product that the cell desires is the 36 ATP. So for a single glucose molecule, you can get 36 ATP if the glucose is completely broken down. And this happens only in the presence of oxygen. That's why we need the oxygen. The byproduct, water, is useful to the cell. However, the other byproduct, carbon dioxide, is toxic, so we must get rid of it. This is why we breathe in oxygen, it is to break down glucose fully, and we breathe out carbon dioxide because if carbon dioxide accumulates in the cell and in the bloodstream, it becomes toxic. Cellular respiration is made up of at least 5 phases, and each phase is made up of multiple chemical reactions that are mediated by enzymes. Because this is so complex, we can try to imagine this process as a ride in an express train, which is the A train, in the New York City subway system. Let's say that we get in at Harlem 125th Street. Then we have Columbus Circle, 59th Street, followed by Times Square, 42nd, Penn Station, 34th, which are all express stops, leading to 14th Street, 8th Avenue, and let's say we get off at West 4th Street. All of these are express stops, and we are skipping the local stops. Harlem represents glucose, Columbus Circle is pyruvic acid, Times Square is acetyl-CoA, Penn Station represents citric acid cycle, 14th Street is the electron transport chain, and the West 4th Street is chemiosmosis. I want you to imagine that you have just attended a really fun birthday party of a loved one. And now you're ready to go home. And so you catch the A train. And you get in at Glucose or Harlem. You pull out your phone and start looking at the pictures that you shot at the birthday party. They bring on a smile. We'll call this positive energy ATP. You find a few pictures that you think you might like to share with your family. These pictures that you captured, we'll call that NADH. We put it in a folder in your phone to be shared with your family later. The train passes pyruvic acid, and by this time you find 1 or 2 blurry pictures and you want to delete them. You delete them, and that would be carbon dioxide. You find more pictures to share, and that would be more NADH. The train passes acetyl-CoA, and you've reached citric acid cycle. You find more blurry pictures or pictures you don't like, and you delete them. At the same time, you find pictures that you love, and you put them in the folder to be shared with your family. You even find a video clip to share, and we'll call that FADH2.
So we have 3 NADH and 1 FADH2, all to be shared with the family. We'll upload all these pictures that you captured to the family group chat. We'll call that the electron transport chain. And during this time, you may find 1 or 2 pictures that you want to save for later. You don't know what to do with them. Maybe you'll share them at a later date. We'll call that water. By the time you reach your last stop, which is chemiosmosis, your family has already seen all the pictures and they are sending you lots of love, lots of laughs, lots of funny comments, and this makes you really, really happy. And this produces a lot of positive energy, which we will call ATP. So chemiosmosis produces the largest amount of ATP.